Okay, hello. My name's George Roberts. I'm a PhD student at the University of Cambridge and sponsored by TOSHIBA. And today I'm going to talk about our experimental demonstration of the differential quadrature phase shift protocol, or DQPS for short. So just to give a brief overview of what I'm going to talk about today, I'm going to start by talking about a number of QKD protocols and their implementations, with particular emphasis on distributed phase reference protocols. Then I'm going to talk about our directly modulated quantum transmitter that we use for a number of QKD protocols. And then I'm going to talk about how we implement the DQPS protocol with this transmitter. So let's start off with phase-encoded BB84, a protocol that's still very commonly adopted to this day. We use phase-encoded through an optical fiber because we have the signal and reference traveling together, so any perturbations to the fiber, both pulses are going to fill, so there's going to be minimal QBA due to that. In BB84, we have two bases, and so we have a signal and reference pulse in a single base, and these travel through the fiber together, but these have to have a globally random phase with respect to every other pulse pair. So one method of implementing this is by using a phase-randomized pulse source, for example, a gain-switched laser diode, and then sending the output pulse through an asymmetric Mach-Zehnder interferometer. So in our implementation, we have a 2 gigahertz signal, so you'd need to have a 500 picosecond time delay to create the reference pulse, and then the signal pulse is created by modulating it using a phase modulator. The receiver, you can have a number of implementations. So here I show an active receiver. So we have a phase modulator to either modulate 0 or pi over 2, depending on what basis wants to be chosen. However, for this, you need to have an identical Mach-Zehnder interferometer delay in Alice and Bob. So you need a lot of stabilization, active feedback to make this work. But there is a full security proof for it. So in 2002, another protocol was introduced, known as the differential phase shift protocol. And this was introduced to be a far simpler implementation for QKD. So this simply uses a coherent pulse source, so you can have a pulse-carved CW laser, and then a phase modulator, for example, a lithium niobate phase modulator, where light makes a single pass through it, and it's modulated by the amount of signal you put through. And this only uses a single basis, and then the qubit the information is encoded in the differential phase between every single pulse. This then travels through the quantum channel, and the receiver is just set to a single basis. You don't need to choose a basis at all. So it's all very simple. But unfortunately, it only has a partial security attack, so it has a seriously degraded performance when full attacks are taken into account. So in order to get around this, a couple of protocols were introduced. So the first one I'm going to talk about is round-robin DPS. This has an identical transmitter to the conventional DPS scheme, but the receiver is completely different. So in the receiver, you have an interferometer with a number of variable delays, and the receiver, Bob, can choose which bits to interfere in a packet, basically, in a DPS packet. Whilst this has a very elegant security proof, and it looks very nice, and a number of innovative groups have come up with methods of implementing it, it is quite complicated. So to design this interferometer is very complicated, and it strays away from the idea of DPR protocols wanting to be a simpler implementation. So another protocol that focuses on the transmitter side of things for DPR protocols is known as DQPS. There's a couple of implementations of this. I'm going to talk about Kawakami's implementation. So this uses 4 encoding states, so 2 bases. So the receiver is exactly the same as in BB84. Essentially, though, you take a coherent pulse strain, and then you separate that into randomized blocks. And these blocks can be an arbitrary length. To implement this is also quite complicated. So you've actually put the complexity back into the transmitter again. So what you need to do is you need a random number generator. So you need a high-speed random number generator if you're working at high speeds. And then you're going to need another phase modulator to modulate the randomized blocks. This modulator needs to be continuous, which is kind of difficult. Otherwise, you're going to get discrete randomizations. It's going to need to have a flat top modulation. Otherwise, the cube is going to increase because at the beginning of your block, the modulation depth could be different to the end of your block. And also, it's going to have to modulate about 2 pi. So it's quite power hungry, really. So now to move on to direct modulation. Direct modulation is a very simple method of laser modulation. You simply change the bias current to the laser diode, and this changes the intensity, frequency, and phase of the output light. You commonly see it used in classical comms for intensity modulation, for amplitude shift keying, or on-off keying. However, when we go and try and use it in quantum communications, there's another complexity added, because say Alice and Bob are trying to modulate the phase of the laser, they're also modulating the frequency of the laser. So they can have Alice and Bob can have a perfect communication in phase, perfectly secure communication in phase, but you've just opened up a side channel that they can use in frequency. So we need some way of filtering out this frequency change and intensity change. The method we choose to use is known as optical injection locking. Optical injection locking is where you have a master laser and a slave laser. Here I show a circulator in between them. You shine the master laser into the slave laser, and the slave laser adopts the phase and frequency of the master laser. Commonly, this is used in classical communication. So if you have a gain-switched laser diode, it's going to have quite a high jitter, high frequency chirp, and the modulation bandwidth won't be great. But it is optical injection locking can be used to ameliorate all of these properties. So you can get a reduced time jitter, reduced frequency chirp, and you get a better modulation bandwidth. The property that we specifically use is the phase inheritance. So we have a gain-switched slave laser diode, and then the master laser is modulated to change the phase of the slave laser pulses. And this has allowed us to create a very simple modulator-free quantum transmitter that doesn't need any interferometers, so you don't need the kind of active feedback mechanisms you would need to implement the BB84 protocol I showed on the previous slide. So how does this actually work? So I show here on the left a CW master laser. So the phase is coherent. So the phase is continuous, sorry, there's no interruptions there. And then the slave laser current, this is for gain switch pulses. The output pulses on the bottom left inherit the phase of the master laser, and that's continuous. There's no phase shift between them. On the right, however, we apply a master current modulation. So this changes the phase evolution of the master laser, as you can see in the second bit there. Now, these two slave laser pulses that are on either side of the master laser modulation are going to inherit a different phase. So we see if we overlap them now, we've applied a modulation to the phase of the output pulses without affecting the frequency or intensity. And just to give a more intuitive view of how we don't actually modulate the frequency, I show here the effect of intensity, the effect of direct modulation on the laser diode. You can see it changes the frequency. So both pulses are either side of this modulation, so they inherit the frequency that's directly above them, which is the same, and the intensity as well, so there's no side channel there. However, the phase is shifted by an amount that's proportional to the time of the modulation and the depth of the modulation. This has allowed us to create arbitrary modulations. So here I show the 4 BB84 states. So this is the master laser power on top in A, the optical power. And on the bottom, I show the output from a 1-bit interferometer. And you can see that we've created the 4 states very nicely there. So previously, I showed this work at QCrypt last year. And we showed that this transmitter has a very low half-wave voltage of 0.35 volts. This is very low, so this is possible because it's a laser, light oscillates through the laser. So if you directly modulate the laser, it changes the refractive index of the gain medium, and light makes many passes through that. Whereas when you're talking about a traditional lithium niobate phase modulator, it only makes a single pass, so the half-wave voltage is more around 5 volts. And the device can be shorter, which is also a positive. So we implemented the BB84 and DPS protocols, both phase-modulated protocols, and earlier in the year, we also implemented an intensity-modulated protocol, the coherent one-way protocol, and got excellent results, so megabit per second key rates. So now on to the DQPS protocol. I mentioned before that if you were to implement the DQPS protocol, you'd need some complicated method of randomizing the phase. Well, with our transmitter, this doesn't need to be complicated, because if you deplete the master laser cavity, then the subsequent emission is going to be from vacuum fluctuations, which are random. So what we can do is we can have a block here. So inside a block, the phase is coherent. You choose a single basis. So here you apply 3 modulations, and then you deplete the master laser cavity, and then bring it back up again above threshold, and then the phase will be coherent again. And as I say, the slave laser pulses will inherit that phase. So then the output of that goes through a circulator. It's attenuated to a mean photon level less than 1, and then it travels through the quantum channel to Bob. And as I say, in Bob, we would ordinarily have a receiver that's identical to the one in BB84. We're just doing a proof of principle experiment here. So we use a heater to choose the basis we measure in. We measure the cube or a number of counts in that basis, and then move to the next basis. And we do this to get at least 8 times 10 to the 5 counts at each distance. But at short distances, we get far more. And this paper can be found on the archive here. So we need some way of proving that the phases are indeed randomized. So what you can do is you can take consecutive blocks and interfere the pulses together. So just put the blocks through the interferometer and measure this random interference here or here. So this is exactly what we do, and we measure the intensity of the output interference. And this fits very well the distribution we'd expect from a random interference through a Mach-Zehnder interferometer. So this should follow a 1 plus cos delta phi distribution, where delta phi is continuously random between 0 and 2 pi. Of course, we have time jitter and measurement error, so this kind of broadens our distribution, especially at the high intensity side. I do a simulation. This is shown in circles, and the experimental data for 125 picoseconds of downtime in the master laser fits very well to the simulated values. I also show here what happens if you don't deplete the cavity enough. If you don't deplete the cavity enough, the phases between the blocks aren't going to be randomized. There's going to be some correlation, and yeah, so that's shown here essentially. So in green, you can kind of see it's not really that, it's kind of skewed towards the left almost. So you need to be quite careful if you're implementing this. I also take the autocorrelation data here, so I just take a number of the random interferences, and you want to make sure that if you know the global phase of one block, it's not going to have any impact on the global phase of the next block. And that's what this shows. So I show 95, you might not be able to see it from the back, but I show 95 and 99% confidence bounds, and data over 100 lags fits very nicely inside that. Obviously, at 0 lag, you're interfering a pattern with itself, so the autocorrelation function is going to be 1. So now to talk about the results we get. It's very simple for us to implement the BB84 protocol with this transmitter. Indeed, you can see DQPS more of a generalization of the DQPS protocol as a generalization of the BB84 protocol. So the BB84 protocol is simply the DQPS protocol with a block size of 2. So you simply have the signal and reference pulse. So I do secure key rate simulations to work out what the optimal block size and optimal mean photon number are at each distance, and then take the data and using the experimental setup I showed a few slides ago. And this is what we get. So on average, the DQPS gets a 2.71 times higher secure key rate than BB84, which is very good. And we also show it over real fiber. These are the points that are stars, so 20, 40, and 60 kilometers over real fiber. The base QBA is very low because the phase inheritance between the master laser and the slave laser are very good. So we get a QBA of just 2%, and we're able to achieve megabit per second secure key rates at short distances and positive secure key rates up to a distance of 110 kilometers. I mentioned before that because we don't have an interferometer, we can make a much more stable transmitter. So I show this here. I independently temperature control the master laser, the slave laser, and the Mach-Zehnder interferometer, and then set the system running, just set it running for 3 days, continually measure the QBA and the raw count rate. And as you can see, this is, it's so stable, at 8 decibels attenuation, so an equivalent channel length of 40 kilometers at 1550 nanometers, the QBA on average is 2.03% with a tiny standard deviation, and it would give no drops in secure key. So over the period of 3 days, this would have allowed us to distribute 4.95 gigabits of secure key material with absolutely no active feedback. So to conclude, we've shown the DQPS protocol implemented using a directly modulated transmitter. It would have been very difficult to implement using other methods. This has enabled us to get megabit per second secure key rates at short distances and has shown stability over 3 days with no active feedback. So now we've shown this transmitter can work for phase modulated protocols, BB84 and DPS. We've shown that it can work for intensity modulated protocols, the coherent one-way protocol, And we've also shown that it can provide arbitrary phase randomization. So essentially, we've shown that this transmitter, with no hardware modifications, only software modifications, so changing the signal into the master and slave laser, can produce any protocol that uses weak coherent pulses, which is very promising for future quantum networks. Can I take any questions?